This is the eye of a trilobite. It's 400 million years old, made of solid stone, and it belongs to the oldest complex visual system ever found in the fossil record. Trilobites ruled the ancient oceans for 270 million years. These marine arthropods were already old when the first dinosaurs appeared. They were already extinct when the dinosaurs were still new. And the most extraordinary thing about them wasn't their reign, or their numbers, or their strange three-lobed bodies. It was what they did with light. Every trilobite that ever lived built its eyes out of calcite, the same crystalline mineral that limestone is made of. The lenses were grown from single crystals of clear calcium carbonate, aligned with such precision that light could pass through them without distortion. No animal had done this before. No animal has done it since. For 500 million years, the only creatures ever to see through eyes of solid stone were these. This is the story of how they built those eyes, why their invention may have changed the course of life on this planet, and how a vanished family of armored sea creatures became the master key paleontologists still use to read the rock record of an entire world. Before we can understand the eyes, we have to understand the animal. Trilobites were marine arthropods, distant cousins of today's horseshoe crabs, spiders, and insects, though they were already their own distinct line of life when the first horseshoe crabs were still hundreds of millions of years away. They lived entirely in the ocean. They never made it to land. And every fossil trilobite ever found began as a creature crawling, swimming, or hiding on the floor of some long-vanished sea. The name means three lobes, and it describes their most obvious feature. The body of a trilobite is divided into three parts running from head to tail: a head shield called the cephalon, a flexible middle section called the thorax, and a tail plate called the pygidium. The body is also divided lengthwise into three vertical lobes, a raised central spine flanked by two flatter sides. Three lobes one way, three sections the other. The architecture is so consistent across the group that you can recognize a trilobite from a single fragment, even if the rest of the animal has been crushed to powder. Most trilobites were small, 2 or 3 inches long. A few grew to the size of a dinner plate. The largest known species, Isotellus rex, reached over 2.5 feet. Beneath the armored shell ran 2 rows of jointed legs and gills, the standard arthropod toolkit, though those soft parts almost never fossilize. What remains is the exoskeleton. And here's the strange part. When trilobites first appear in the rock record, around 520 to 530 million years ago, they appear already fully formed, already armored, already three-lobed, already, in many cases, seeing. They didn't evolve in front of us. They simply walked onto the stage. If you want to understand what we mean when we say a living creature has become a fossil, how an animal ends up as a piece of stone you can hold in your hand, our video, What is a Fossil? The Ultimate Beginner's Guide, is the place to start. Building an eye out of stone is a strange thing to do. Most animals that evolved vision did it the obvious way: soft, flexible tissue that can grow, change shape, and focus light by warping the lens. The trilobites went in the opposite direction. Their lenses weren't soft. They were mineral. Each lens was a single crystal of calcite, the same substance that limestone, marble, and seashells are built from. Calcite has a useful property. In pure crystal form, it's transparent, but it also has a less useful property. It splits incoming light into 2 beams, producing a doubled, blurred image. Anyone who has held a clear chunk of Iceland spar to a printed page has seen the effect. The writing appears twice, slightly offset. For a predator trying to track prey, that's a death sentence. The trilobites solved the problem with geometry. Every lens they grew was aligned along its own optical C-axis, the one direction through a calcite crystal in which light doesn't split. Hundreds, sometimes thousands of these lenses sat together in a single eye, each one a tiny pillar of clear stone, all rotated into the same correct orientation. To do this consistently, across thousands of separate species, across 270 million years, is one of the great structural feats of evolutionary engineering. The oldest known compound eye in the fossil record belongs to a small Cambrian trilobite called Schmidi-Ellis rete, recovered from rocks in Estonia about 520 to 530 million years old. Detailed analysis of this specimen, work built on by researchers including Ewan Clarkson at the University of Edinburgh, whose foundational studies of trilobite eye structure remain central to the field, confirmed that by that point, the basic design was already in place. We call this design the hollow crowal eye. It's the ancestral form, the way trilobites saw at the very beginning. Hollow crowal eyes packed hundreds or thousands of small lenses under a single continuous cornea, set in tight hexagonal patterns like a compound insect eye. Most trilobites that ever lived saw the world this way. But then, around 480 million years ago, in the early Ordovician, a single suborder called the Phacopina did something nobody else has ever done. They invented a new kind of eye. The schizocrowal eye replaced the thousands of small lenses with around 700 large ones, each lens given its own cornea and separated from its neighbors by thick walls of dark cuticle. The result was strange. Large, bulging eye towers studded with discrete crystal lenses, each one staring out independently. It has no real equivalent anywhere in the modern animal kingdom. The placement and the all-around field of view suggest the schizocrowal eye wasn't a hunting tool, but a defensive system, an early warning network for spotting predators coming from any direction. Phacopina trilobites carried this eye through nearly 170 million years of the Paleozoic before they, too, died out. Here's the strangest footnote. In 500 million years of evolution since the schizocrowal eye disappeared, exactly one other animal has ever come close to reinventing it. A tiny parasitic insect called Xenos pecii, a member of the order Strepsiptera. That's the entire list. Trilobites and one bug. Everything else with vision on this planet went a different way. It's one thing to say the trilobites saw first. It's another to say the world had to change because they did. In 2003, the British biologist Andrew Parker proposed an idea that has come to be called the light switch hypothesis. His argument was that the Cambrian explosion, the strange, sudden burst of complex animal life that begins around 540 million years ago, wasn't driven primarily by a change in chemistry, or oxygen levels, or genetics. It was driven by vision. Once one animal could see, every other animal had to deal with the fact that it could be seen. Before vision, predation was mostly a matter of bumping into prey by accident. Once vision existed, prey could be hunted from a distance. A predator with eyes could choose its target. A predator with good eyes could choose its target across open water. Every species that wanted to survive against that predator suddenly had a problem to solve. Some grew armor. Others grew spines. A few learned to burrow into the sediment, or to glide in mid-water, or to evolve camouflage. Many learned to see for themselves. Within the geological blink of an eye, the simple, soft-bodied biota of the late Precambrian gave way to a riot of shells, claws, segmented bodies, swimming fins, and complex sense organs, the basic body plans of nearly every animal alive today. The fossils that make this argument most vividly come from exceptional preservation sites called Lagerstätten, deposits where soft tissue and fine anatomical detail survived alongside hard shells. The most famous of these is the Burgess Shale, a Cambrian fossil bed in British Columbia that captures the full ecological complexity of the early animal world. Predators, filter feeders, burrowers, swimmers, all appearing together in the rock at the very moment the explosion was underway. Trilobites are present in the Burgess Shale. So are the animals they hunted, and the animals that hunted them. We can't prove that trilobites alone flipped the switch. Other early Cambrian predators almost certainly had eyes of some kind. But trilobites are the first animals whose eyes we can actually see in the rock. The first ones we can study, count. and measure, and they appear at the precise moment the diversity curve begins to climb. They weren't just present at the Cambrian explosion, they were very likely part of what made it happen. This is the deepest claim a video about trilobites can make. They weren't just weird marine arthropods that happened to do a strange thing with calcite. They may have been the species that introduced sight to the planet, and in doing so, written the first chapter of every visual animal story that has unfolded since, including ours. There's one more thing trilobites did that earned them a permanent place at the center of paleontology. They fossilized, and they fossilized often. For 270 million years, trilobites left their armored shells in the seafloor. They lived in every ocean basin on every paleocontinent. They came in more than 20,000 known species, from the early foundational order Redlichida, among the first trilobites to appear in the Cambrian, through to the last survivors of Proetida at the end of the Permian. They evolved fast, with species replacing species across short geological windows, and they shed their exoskeletons, a process called ecdysis, many times during their lives, which means a single living trilobite could leave behind half a dozen separate fossils before it ever actually died. Combine these traits and you get something paleontologists call an index fossil. The three criteria are simple. The animal has to be common, it has to be geographically widespread, and it has to be specific to a narrow window in time. Trilobites check every box, and they check them harder than almost anything else in the fossil record. Find a particular trilobite species in a layer of shale in Tennessee, and the same species in a layer of shale in Morocco. Without any other evidence, without any other tool, you can prove that those two slabs of rock were laid down at the same moment in Earth's history, on opposite sides of an ancient ocean. This is the discipline called biostratigraphy, and trilobites are its founding witnesses. Geologists used trilobite zones to map the Cambrian, Ordovician, Silurian, and Devonian long before anyone could date a rock chemically. To this day, the boundaries between several Paleozoic stages are defined by the first appearance of a particular trilobite species in a particular outcrop. The animal is gone. Its body has been replaced, atom by atom, with mineral, but the timestamp it left in the rock is still legible. That's why every fossil hunter starts with trilobites. They're abundant. Morocco alone exports thousands every year. They're cheap, they're recognizable. And once you understand how a trilobite became a fossil, you understand the same process that turned every dinosaur, every ancient fish, every petrified leaf into stone. Our pillar video, What is a Fossil? The Ultimate Beginner's Guide, walks through that process in full, and trilobites are the textbook example. For all their dominance, trilobites didn't last forever. The decline began in the Devonian around 360 million years ago, when a series of extinction events, still not fully understood, wiped out nearly every trilobite order. By the end of the period, only one group remained, a small conservative order called Proetida. The schizocrolide Phacopina, with their impossible crystal towers, were already gone. Proetida held on for another 100 million years. They weren't flashy or especially diverse. They were the quiet survivors of a kingdom that had once owned the seas. They lived through the Carboniferous swamps. They survived the rise of the early reptiles, and they kept going right up until the end of the Permian period, 252 million years ago, when the worst mass extinction in Earth's history, the Great Dying, killed roughly 90% of all marine species in a span of geological moments. The last Proetida went with them. After 270 million years of continuous existence, the trilobite line ended. What they left behind is what this video has been about. 20,000 named species in the rock. The first written record of vision on this planet. The textbook example of how an organism becomes a fossil. And in many ways, the foundation of the entire science. If trilobites had never existed, we'd have a very different and much poorer fossil record. We'd also, in all likelihood, have a very different theory of how complex life began. For anyone who wants to start at the beginning of that story, our What is a Fossil? The Ultimate Beginner's Guide is the entry point. Somewhere in a slab of Devonian shale or Cambrian limestone, the eye of a trilobite is still staring out of the rock. Made of stone, aligned along its C-axis. 400 million years dead and still seeing.